Okay, so welcome you all for another session of this daily lead code practice. And we have easy, medium, and medium today. So let's start with the first question. Let me share my screen. Okay, so I hope everyone can see my screen.
Yeah.
Okay, thank you. So the first question is, it's binary tree level order traversal 2. So the last time which we did, we have traversed the binary tree from top to bottom, and we need to return the children at every level. Now we need to uh, now we need to do on the reverse basis. So similarly, level order, but in a reverse way. Anyone has tried this particular problem?
I did it as similar like last time, do the level order traversal top down, and once I
Yeah.
got the array result, then I reverse it.
Yeah, that's one approach. Even I think about that only, like just do the level order like top down, like how we did last time, and just reverse the list. Anyone has any other idea? That's a nice approach, I would say.
We can also do the depth first
Queue.
search.
Yeah.
Okay.
Using a queue.
Queue with the depth first search?
The recursive method is the depth first search, right?
Yeah. So someone is saying we can use the depth first search. How?
Okay. I did using the recursive way.
Oh, yeah. So how you have done that?
I think this was similar to what we discussed, the binary level or the traversal one, where you
Yes.
just recurse the right node for a left node and the right post order traversal basically, and then add it to your result list.
Yes. And now we just need to do it in reverse manner.
Yeah. I think post order traversal, the previous case we did level order.
Yeah.
I mean, in order, and in this case, we'll do the post order traversal.
Okay. Post order using, post order
Just
using a
recursion.
recursion.
Yeah.
So you are just appending that in a list, whatever you are getting.
Yes. Yeah. Every level you have a new list.
Yes.
And then you add it to your main resultant list.
You have done that? Can you share the code or something if anyone wants to see it?
I am on my phone. I can share it later, or if someone else has coded.
Okay, anyone wants to go with another other? Thank you so much, Smita. That's
Sure.
one approach. So anyone wants to discuss? Yeah.
I was thinking if this can be solved using queue as well. I haven't solved this, but it just came to my mind.
Okay, for queue,
like the
I think
BFS.
for queue, what I would do, like while traversing each level, I'll just append in the like first position, like how we are appending at the last position. We
Right.
just starting appending in a result list or a main list at a starting position each level. So while we reach at the end of the level, we can that level would be at the first in our result list.
Okay.
But I don't know how much the complexity F inserting at a particular index, like at 0, and pushing all other lists towards the end. So that would be a, I think, uh, time complexity would be there, because uh, I'm inserting at the first position and pushing all the other lists uh, back. So that would be an extra cost.
Okay.
So there's two way, right? First, we can, first we can put it into an array, and when we have it, we reverse the array of lists,
Yes.
right? The second way I think of is, instead of have the array of lists, we can have like kind of a linked list. Okay, we have a linked list, and each element in the linked list, it is an array. So because, yeah, so that, if we in that way we can insert it. I mean, we can prepend to the linked list that take constant time.
Yeah, so that's one, like, rather than taking a list, taking a linked list would be easy, so that you can insert at the first, like ahead of it would be easy,
Yeah.
and it would be order of one approach, like inserting in a linked list at particular index, I think. Anyone wants to?
A little tricky to know, when you need to create a new linked list.
Sorry?
It's a little tricky, if we go that way, to know when would you need to create a new linked list, right? Because if we go top down, we know at every level, then we can create a new one. But if we do reverse way, then it's a bit tricky, I think.
Using a reverse
logic?
Okay.
No, I'm talking about we're using the linked list instead of an array.
Yeah,
right?
yeah, that would be a little bit tricky, but can be done. So one is like another approach would be, I'm thinking of using a stack while doing in an iterative way. Anyone has used stack solving this problem?
Stack would be similar to recursion, right?
Yeah, instead of doing a recursion, we are putting in a stack.
Explicitly.
Yeah, that would be in an iterative using stack. Anyone wants to elaborate on this?
Yeah, with the stack, if you do recursion, I'm not sure if like you can quickly access the middle element, in the stack. Because with the stack, if you go do the recursion, then at each depth, we need to create a new array, right?
Yes.
Then it's not easy to access the middle element in the stack.
Yeah, that is one thing.
But I believe like that is true only when if we are doing BFS, then the stack should work. Because doing the BFS, the current level is always on the top of the stack.
Yes.
BFS with the stack?
No, like we will do the BFS with the queue.
Okay.
Okay, but for each level, when we are storing the list for that level, we will put them in the stack.
Yeah, and when we are after that, when we need to return our result, then we'll just pop out from the stack and just put it in a result in an array or a list and just return that. Is that a way you are saying?
Yeah, but that wouldn't that be like an extra data structure we need to use, right? Because
Yeah,
now we use an extra stack, versus that we already have an array to return.
but if we are saying that if we have a result while solving in a BFS, we'll be storing in a result, just reverse it. Which complexity is higher? Reversing it and then returning it, or just putting in a stack and then popping out and then returning it?
Reverse is constant time, right?
Uh, Reverse would be like,
Why reverse is constant time?
yeah, why?
Right, it's not constant time. I mean, it's big O of n, right? But
Yep.
yeah.
I think like if you put like in a linked list, that is fine. You can just insert at the start.
I believe like
Okay.
where the trade-off like we are trying to look into is using extra memory versus like just reversing. Like if we have to use the stack, definitely like we are using extra memory. Okay, and then what we have to do, we have to again traverse the whole stack
Yeah,
by order of n to create a array list that we want to return. Okay,
yes,
in the other way like which is suggested by just using a list. Okay, put them in the order from top to bottom, and then reverse the elements in the same array. Okay, which will be we are not using any extra memory. Okay, and reversing the array is same as order of n as traversing the whole stack.
No, but I was telling like put in a linked list and always a bank in the start.
Yes, but again you have to traverse the whole
No,
list.
then I will always put my new result in the start.
Agree, but see the result like we are returning list.
Yeah, if I think I can. So linked list is inherited from list
Okay, then
interface in
okay,
Java.
yeah, then it's a different case then.
I think so. It might work because like a linked list is also inheriting from list interface. So then I don't need to like. I'm just throwing some ideas.
so you are saying inserting at always at a first would be order of n operation in a linked list, correct?
Yes. No. Inserting would be a constant time, like order of m1.
Oh, sorry. Yeah, yeah, order of one. So
Yep, I just verified that in Java, linked list implements the list interface, so which is true, but
yeah,
it might not be true for like other programming languages.
I don't know. Because Python does not have anything like an array list or linked list. Everything is a linked list there.
list. Yeah, everything is a list in Python. So
And .NET, let me think. .NET also has something like similar.
I believe like we got multiple solutions. Why not like
yeah,
try it out and we can move on to the next question.
yeah, we should move on the next question. Thank you so much. And okay, can you all see the second question?
Yes.
Okay. So what second question is, we have given a board like and with all the characters, and we need to find the particular word like this if it is present in a grid or provided board or not, and we can move um, horizontally as well as vertically, like adjacent cells we can move horizontally as well as vertically, right, left, up and down. So, and the main thing is the same letter may not be used more than once. So, for example, here the word is A, B, C, C, E, D. While traversing over here, A, B, C, down C, E, and D, we got an answer, and this is true. Similarly, S, E, E. So from starting over here, or if we can say if we have one S over here, if we go above, down, right, left, we can't see the E. So we just return false and we'll be moving further. And here we got C, and here we can say start with S, then E, then E. Then it will be true. And if we are over here, A, B, C, B, we have given the A, B, C, B. From here, A, B, C, B is not present. Similarly, over here also we have A, and if we start traversing from over here also, we are not getting an answer, so it is returning false. So this is a basic problem. Anyone has tried? Like I tried. Any approach coming in their mind?
I do
Something similar
the
which
I
we
did
did
the depth
yesterday.
first search.
Sorry, there is two people are speaking.
I'm sorry. Go ahead.
Go ahead.
No, I was saying that I'm doing the depth first search.
Yeah.
So for each cell in the matrix, I do the depth first search and try to find if it match the word.
Like moving a depth first search, if we found a word, we'll be returning true. And what if the case we didn't find the character which we are looking for it?
Then
So
we
what
we move to the next cell in the matrix.
And we need to do the backtracking as well.
Yeah, for every cell we need to do the no backtracking, just like depth first search, from that cell.
So basically, if we used a cell in one path, we can't use that again. So basically, in this example, if I'm going from A, B, and then going F, and let's say I'm going S, A, B, F, S, then I can't take upper A. So
That's
basically,
true.
we have to also account like I have visited that person. And if I couldn't get the answer, I have to make it unvisited. Like we did something similar yesterday also.
Yeah, we did with the backtracking problem only.
Yes, take the first case where we start with A, B, then C in the first row, and then C at the bottom. Okay, like in the middle row, and then like E, which is in the last row, and then from there, let's say instead of going left, which is D, what if we go to the right, which is E?
Yes.
Okay, so we go to the E, then we see, okay, it's not matching, then we backtrack, and then again go back to the same E, and then go maybe left from there. So it's a very classic DFS with the backtracking problem.
Yeah.
Very similar to the one that we discussed yesterday, where we have to go from number 1 to number 2 in a 2D matrix, covering all the zeros.
Yeah, similarly like that.
That has one more constraint that we have to
pass all the zeros over there.
Yes.
Yeah.
But the base idea is like very similar.
Yeah, base
Yeah. Like their end condition was we need to complete all the zeros. If it is not completed, then we are not returning an answer. So over here, if we complete all, like if we have reached the length of the word which we need to find, then we got an answer. So basically it's like that. So I had solved this. If anybody willing to see, then I can open it up. So,
Is
but
there a different approach than the depth first
no, no,
search
it's
or
similar depth first
backtracking?
search, depth first search with backtracking. It's the
No,
approach which.
I think the question is like, is there any other approach?
Oh, okay. Anyone has tried any other approach? I'm curious. Breadth first search will not work over here, correct?
Because we want to go in depth.
Yeah.
It works too, but it takes time, and it consumes extra memory.
Mm-hmm.
Yeah, that's also true. And so what if we have various words and we need to find all the words like in
I
that
think,
grid. So for example, these are all the words which we have provided, and we need to tell what all the words are present in that grid.
so I think you are looking for, there is a, I think similar question, word search 2, or probably you can open, it should be down somewhere. But before we discuss that, is there any uh, doubt or confusion on this approach using DFS?
Yes, like and also like how the VFS will work here. If you want to like elaborate like more on it.
Sorry?
BFS, I think how it will work, you'll start from A, you start visiting your neighboring nodes, and every time you visit, at every level, you try to see, are you going in the right direction? For example, what will be the neighboring nodes? A, B, A, S. Then AS is not AS could not be a candidate because the given word is A, B, C, C, E, D. So AS, we will not put that in the queue. And we'll put AB, and we'll also put B's index. B's index is 0 and 1. Then from B, now the string which is in the queue is AB. From B, I can't go back A. I can go F, C, C. I can go A. Can't go towards A side because that is visited. I can go towards
C and F.
C. I can go towards C and F. So if I put if I take F as a candidate, it won't work because there is no F at third position, at third level, I will say in BFS. I'll ignore that and then take C.
So
Then it will become ABC
so
in my queue.
in these scenarios like we won't put the neighbors in the queue unless like they satisfy the condition.
Yeah, if they qualify, then only put the
Yeah.
neighbor in the queue.
It will be requiring extra memory over here
No,
then?
in DFS also we are doing extra memory as stack.
Yeah. So here also will be like if we take a queue, we are taking a queue, then also it's but you are saying we'll not put the neighbors which is not
Yeah,
qualifying.
which doesn't qualify.
Okay, we'll not put them. So while putting in a queue, we'll be just um, like make a string like something
Mm-hmm.
to append in a queue.
Yeah. Make a string, or even we don't need to put a string. I think we are going level by level,
Mm-hmm.
so we can even just put the next, what would be the current index should be in the queue. So first it will be A, then it will be index of B, then it will be index of C, then it will be another index of C. So we'll go one by one, like from there, can I visit my neighbors? It's something like that.
So I have a question.
Mm-hmm.
So let's say at any given point of time,
Hmm.
two or three neighbors are satisfying the condition.
Yeah,
Okay.
so we have to go in all
Yeah,
directions then.
to keep it simple, let's say two neighbors are satisfying the condition. So as per the algorithm, like we will put like those two neighbors. Okay, but let's say the condition, like the constraint, or later on, like we find out that one of the neighbor okay, which we thought may lead us to the solution, okay, is not working, like not leading us to the solution, but the other neighbor will lead us to the solution, but it will go to some path, but, and also
Oh,
other neighbor,
which
okay,
is already visited.
which is already visited. So, so in these scenarios, like I believe when we are pulling them out, we have to make sure we are unmarking all the neighbors which are not satisfying the condition,
Okay,
and
okay.
and we have to go all the way back. Okay, so let's say like A, B, C, E.
Mhm.
Okay, and A, B, C, E on the first row. I'm just like taking some arbitrary example, and
Mhm.
we also have like A, B, C, E, like in the first column.
Mhm.
Okay,
Mhm.
so so while we are going to A, B, C, E, like in the first row, we figure out, okay, it's not going to satisfy our condition. Okay, then we have to backtrack from there. We have to like remove E, C, B. We have to mark all of those unlisted. Okay, because maybe while we are going through the column, okay,
Mhm.
um, there is a path, but that path may include the letters which are on the in the first row. Okay, so I'm not sure like in
Yeah,
this
the
scenario the
backtracking.
BFS will work or not.
So we
I,
need to in that BFS. Actually, the problem is we need to backtrack all the elements while going back.
Yes.
yeah, it
Yeah.
may because there could be path that overlaps,
Yeah.
and when we backtrack, and let's say we mark it unvisit, then later, when we go again, then we go the same path again.
Yep.
Uh-huh.
So
Yeah,
I
so then. Mhm.
It
yeah, I
should take
doubt.
more time.
Yes, I
It, it,
doubt.
it will not go into infinite loop, I think, but it would take more time.
Yeah, time complexity would be high.
No, but I don't think like the back BFS like will work over here.
Yeah, BFS will be tricky here.
Not tricky.
Like.
Like I don't think like it will work.
Mhm.
Why you think it not work?
Because let's say like we are like into some path, maybe deep down, and then we found that like that path doesn't lead us to the solution. Okay, then we have to find a way to mark all the nodes in that path as unvisited. Okay, because if we are in the DFS, okay, we have this uh, recursion stack which we can roll back to and like keep marking all the nodes as unvisited up until we are at some higher level from where we can go to another direction. But in case of BFS, we have to keep track of the path that we came from. So in that case, like we have to mark all the nodes in that path as unvisited, so we can use them later while we are coming from some another path. Does that make sense?
Because let's see if you at B right now, right, at the row 0 and column 1, and let's suppose that two C, one on the right and one on the bottom, right? So you would save the coordinate of that 2C on the queue, right? You save the coordinate of the neighbor on the queue. Then when you process one path from one neighbor, if it does not work, now you process the path from the other neighbor, because you have both of them on the queue.
Okay, but I need like I believe like we have to take an example.
And I think because each neighbor have unique coordinate, I mean a unique row and column. So it would take to it would take us to different path. That means it potentially it could take us to the solution.
We need to take an example, otherwise it won't be clear.
Yes.
So
Okay. Can I share the whiteboard? Okay.
Because you're looking for an example where there are two different paths, and also we need
to come back
to some of the nodes in a path which doesn't lead us to the solution.
So put A, B, C, D.
Or maybe, hey Sonia, instead of like writing, maybe just use the lead code bold, like the solution area. So maybe you can copy paste the letters. It should be easy.
Oh, okay.
Yeah.
I'll just do that.
Because if you have to like modify, then like it should be easy to like modify at that location. So just like share your lead code window.
Okay, yeah, I'll share that only. Okay, so
Yeah, maybe
I'll
like you can write it at the.
So we just need to append over here, for example, D.
Yeah, and just to make
So the main thing is, let's see, we are looking for.
Just to put instead of F
with C.
Instead of F, put
C there, right? Because they both have the same neighbor.
C, and your word is A, B, C, C, B.
C, C, E, D. Okay.
ECCB.
Yeah.
So for example, in a queue, first of all,
it would be A.
Okay.
No, but like this solution is not going to work because we need another B here because we only have single B.
Yeah. So let's say we have A, B, C, C.
S, that file, A, B, C, C, S.
Yeah, A, B, C, C, S.
Okay.
Now let's put it on the queue. Put A, let's say we start from the A first, right?
Yeah.
So then A is gone.
Yeah.
So you can put AB now. And then you can put
C, which is down one.
So both the C's can come, ABC and ABC. Two ABCs can be in the queue now.
So I'll pop it up.
Yeah. And then put ABC.
Okay, ABC and one more.
And then there will be another ABC.
You only put C, right? Because let's say you have A in the queue, and when you take it out and you look at the neighbor of A, and now the neighbor of A is B, then we only put B on the queue.
Yeah, no, for simplicity, we're just putting like how the flow would be.
Okay. So now we have put the neighbors of ABC and ABC, which B has 2C, right and down. So we put that in a queue.
Yeah, then so that ABC is next to the first row one ABC.
Yeah. So first first is this ABC, and one is then AB and down C.
Okay. So now you remove the first ABC, and then you can.
There is a D also.
Yeah, D we can't go.
Yeah, so I'll go with the down one, which is C.
Which is ABCC.
Okay.
And now the first ABC will leave the queue.
Yeah.
And it can't put ABCC. It cannot put ABCS.
Because we need another C. It can go with the that C also.
But that C is visited, if you see. So that's
Okay.
what I think Gaurav was telling. We have to unvisit it if we are not using it.
But you have to consider the backtracking. So when you will go back, you
Yeah.
can.
So this is like not a DFS solution we are discussing. It's a BFS where backtracking could be. So here what we are discussing, like in BFS, can I do a backtracking?
So yeah, so that's why Gaurav is saying we need to unvisit it before moving further.
And
Yes, Tony, I shared like one good example.
Okay.
Okay, like if you take a look at the chat.
Yeah, I got it.
Like just give it a try, like with this example.
So okay, and our target is to reach
It's in the chat.
yeah ABBCB. So ABBCCB. So
take the example in this case, like this solution. Okay, first column ABBCC.
yeah,
Okay, and the only solution that in this case is ABB. If you go to the top row, okay, ABB, and then we have to go down CC, and then all the way to the left.
yeah,
Okay.
that's an answer.
Yes, that's an answer. But in this case, like what will happen if we start exploring ABBCC, which is the first column? Okay, so while we reach the bottom row, while we are exploring the first column, okay, we find that we don't have a solution, so we have to roll back, backtrack all the way back to the A, and then mark everything unlisted.
So for example, the first column is ABCC over here, but we need one more B and we can't reach over here. So we need to all the way go back and need to start again from here.
Yeah, try that algorithm, like how the BFS will work. Like,
so
like
here
from the start.
It won't work until we go back and clean the things.
Yeah, we need to, that's why I'm like, if we are coming over here, it will start from here, A, B is right, then B, C is right, C is right. And, but we reached, we need one more B and it is not here. Like all the children of last C doesn't contain any, or children or the adjacent cell doesn't contain any B. So it needs to traverse back all the way and check another like B.
Otherwise, it won't let the other solution to use that B.
Yes.
So I believe like the BFS will work only in this case if somehow like we keep the route that we are coming from. Okay.
Yes.
So
Yeah.
once we figure out, okay, we don't have a solution through a certain path. If we know the route that we came from, then we can unmark like all the way to the wherever needed.
The thing is like then every one has to maintain their own route.
Yes. So
they can't share like a common visited matrix or something like that.
Yes. So that's why I'm saying like DFS is a straightforward solution. BFS may work. I'm not sure like it will still work or not, but we have to add like a lot of additional logic to make sure we have to backtrack. Okay, mark everything as unlisted, and up to what point we have to mark everything as unlisted.
Yeah, because you need to track which index or which value you visited, right? Because you don't want to keep going on to the same value again and again.
So also one thing is like if we are traversing all the way, like if we are reaching to one path, going for one path, and its neighbors, we need to say that all like this is also these are the neighbors of these are the neighbors of B, and then this is a neighbor of again B. So, but we are going to the neighbors, but the initial neighbor would set in a queue so that it should not we should not remove it also. That's also a constraint, I think. So for example, if I have put A's A, B and one more A, B, so because the neighbors are A, B and A, B, and here all the way we, and if it is not reachable from this particular path, then then uh, then this would be unmarked and then it would be going back over here. So but the thing is we'll be reaching if side by side another path is also going on.
So basically, we don't need to do this visited thing. If I have to do a BFS solution, I won't maintain any visited thing. I'll find other way so I am not stepping over the things which I have already done.
But one thing is, like, if we are traversing, if another path is going over here, and when it is reaches towards here, B,
Yeah, I
but
can use that B.
already listed.
So basically, instead of putting a index in the queue, I will also put two things in the queue: a set of all the things which I have visited, something like that, or I will come up with a pattern. So if you see here, if I go from A to B, my either I'm going in one direction, like my index is increasing. So somewhere there would be a pattern, like either I'm going up or I'm going left, right, bottom. So I can use some kind of pattern to identify I'm not going back.
Yeah, we need something to think about it.
agree
I
with
think
that.
we should move on for the next
Yes,
question.
yeah, let's do
And
that.
yeah,
But this
so
is a good discussion. Give it a try. If there is a solution, like please post it on the Slack so everyone can benefit from it.
yeah, exactly.
And meanwhile,
But
can you want to follow up on the other one which we are discussing, word search too?
I think we have just 15 minutes and we need to go for the last question. So that's I can show just one that like this is another problem similarly like this. Sorry. And what it is,
So basically here, I think we just want to find every word.
yeah, so we have given a words and we just need to find the word which exists in this grid. For example, over here, oath and eat exist. So our output are those words which exist. Like how we returning a true, we need to return the true values which are existing in a, we need to return the strings which are existing in a,
So I think one approach is like take each word and do the same operation which we did in the last.
yeah.
Uh,
So that's the particular approach, I think.
but is there can be a because now what I'm doing, like I'm taking one word and doing the entire operation. Then so basically the complexity would be if there are m words and the grid is n by n, the complexity would become m into n into n.
Yeah, because we need to traverse all the words and we and the complexity also and as well as all the space complexity also.
Space would be like kind of constant only n by n. We'd be reproducing the same visited one.
Yeah.
Or yeah, if we are doing a stack solution, yes.
Hey, I believe like we can move to the next question because
Yeah, so we should move on the
this
next
is like
question.
a entirely different question. Maybe we can take it like next time.
Yeah, thank you. Okay, so you all see my screen for the last question. So the question is find the city with the smallest number of neighbors at a threshold distance. So we'll be providing this kind of a edges. Let's start with an example only, then it's more clear. So we'll be providing the n that's saying that we have n cities, which is like what zero what this depicts is zero is a starting point, like zero from where it is starting, and one is where it is reaching, and three is the weight. And we have given the distance threshold of 4. So if we are reaching at particular point with more than with more than the this distance thresholds, will not be including that. For example, over here, from 0 it is reaching 1, 0 it is reaching 1, and 1 with 3, and 1, and then it is reaching 2 with distance of 4, so which is included, because 4 can be included, which is a threshold. So that's why it's written that city 0 can go to city 1 as well as to city 2. Similarly, at city 1, we can go to city 0, city 2 as well as city 3, because all the weights are in the range of 4, like threshold. And then city 2, we can go to city 0, no sorry, city 0, because 1 plus 3 is 4, and city 1 as well, which is 1, and city 3, which is 1. But from city 3, also we can reach to city 1 3, which is 3, and then from city 3 we can reach to 2, which is 1. We can't go from 0 to 3 because it will exceed this the, the threshold distance, which would be 7, so which is more than the path, so will not be included. And what we need to return is, we need to return the minimum cities which we can cover in that threshold. For example, over here, cities 0 and 3 have 2 neighboring cities at a distance threshold 4. So they return 3 because it is the greatest number. So if we have the same number of cities, then we just need to return the number which is the greatest one, which is 3. So everyone understands what the question is saying? Any doubt about the question?
I believe like no.
Yeah. So what would be the approach comes first of all in a mind, like how
So
this problem is.
I think we did something similar question few days back, where something like flights was there, and we used this Dijkstra something, find
Yeah.
minimum distance or like shortest distance. So I think it could be used here also, and yeah, so it can be used here from 0 what was the nearest cities, and then
Yeah,
this
because we
threshold.
are, and Dijkstra used for like, so I think used for minimum also. So here also if we are looking for the minimum
No,
cities.
we are not. So basically, Dijkstra gives you the shortest distance from one city to another.
Mm-hmm.
So here we are trying to find all the cities within the threshold. For
Yeah, within the
example,
threshold
zeros
or the
from
minimum
0
city.
it will give city 1 and city 2.
Yeah, but yeah, city, like the minimum cities in a threshold, like return the city with the smallest number of cities that are reachable through some path.
So what's the
Yes,
first goal here? We have to figure out the shortest path from each city to every other city.
yes.
Yes, and within that threshold.
Within that threshold, like maybe so as a first step, like path from one city to other cities.
Yeah, so
Minimum.
Yeah.
minimum path from, for example, from this, where you can go,
Yes.
from here, where you can go at that threshold.
So from 0 you can go to using two paths,
Yes.
0 1 2, 0 1 3 2, but the minimum is 0 1 2.
So what's
So
the good algorithm like for figuring out a shortest path from given a source to destination to like maybe all
Or
the
all destinations.
all the nodes.
So
So
here we can say that we can't reach 2 from while traversing from 1, 3, and 2, because we'll be calculating by that will be the calculation of 5, which is more than the
Yeah.
threshold. We can
So we
directly
already talked
go.
about like the digester algorithm. Okay. Which, yeah. Given a
Yeah.
source, we can find the shortest path to all the nodes. Okay.
Mm-hmm.
Uh, what about like finding the shortest path from every node to all other nodes?
every node
to all
to
other
all
nodes.
other nodes.
Cause we here, like, that's the goal. We have to, we are like not given only one source, but for each city we have to find out the neighboring cities, okay, which are under a threshold, or under or like equal to the threshold.
Yeah, and one more thing, this is undirected graph. So if we are going from 0 to 1, the 1 to 0 also
Yep.
included.
So yeah, so basically, if with for this first approach of Dexter, what we have to do, like start from every node, get the same thing what is mentioned in the in the example. If you go a little bit down,
Yeah.
And anyone else like have a thought on this problem?
I have only this thing like do Dexter. I know there are other algorithms also. I think we discussed last time also. Forget its name, Floyd-Warshall algorithm. I think Roger mentioned that. So that can account from every node to other node, and that also take account if there are negative weights also, because Dijkstra can only work
In
if
a
there are
positive,
positive weights.
I am not sure about the other algorithms.
I think he mentioned about Bellman-Ford. I remember when he mentioned Dijkstra, he had mentioned about Bellman-Ford algorithm also, but I don't
So
think.
Bellman-Ford can again will take one node at a time. So let me repost his.
So do you remember the what algorithm is about? Bellman-Ford?
Oh, I think Puneet said Floyd-Warshall.
Floyd-Warshall also.
Sorry.
Yeah, Floyd. So I'm going to repost that.
So
So I'm going to.
So this problem has a constraint that like all the weights are non-negative. Okay, so the good options are Digestra and Floyd-Warshall.
actually, anyone is not aware about the Dijkstra or Floyd-Warshall.
So there are seems three algorithms: Dijkstra, Bellman, and Floyd-Warshall.
That would all those would be useful in this particular question.
Yes. So I'm also going to put like what we discussed last time in the chat. So it was didn't get proper.
So it's saying Dijkstra is a single source, and it would be
Yeah,
to
it says Dijkstra single node,
yeah.
uh,
Bellman is also single source.
but it takes negative edges. But the complexity of Bellman is the order of vertices and edges.
Okay. So how it is differentiate like Floyd-Warshall is using all the pairs. It can use all the pairs.
Hey Sonia, like if you scroll down a little bit,
Yeah.
like there is a constraint given, like how many edges are there in this question?
So there are edges.
Like n square edges.
Yeah, and square. Yeah. And
Okay.
one more thing, we have a nodes from 0 to n, which is like if we are traversing as well, we can start from 0 to
Yes.
n.
So I think like given this constraint, like we have n square edges. If we look at the chat that you posted, okay,
Yeah.
the Floyd-Warshall doesn't depend upon the edges. Okay, so Floyd-Warshall will perform in if number of nodes, like n is number of nodes cube, so order of n cube. Okay, but if we take a look at Digestra, okay, it says e log e v times. Okay, e log e. Okay, number of edges here are n square, and then we already have a like a vertex into multiplication. So I believe like Digestra will be slower here because it will be n cube log e. I'm just like looking at the solution, the time complexity. I'm
So
not
your
very much aware of these algorithms.
dicuspla would be n cube log
E, E,
e.
E the number of edges, because the chat that you posted, it says E log E B times.
Yeah.
Okay, so we know that E is n square. Okay, yeah. So yep, Puneet posted that it will be
Yeah.
V cube, like number of vertices, n cube. Yeah. So I believe like the Floyd Warshall should be the right approach here, because we don't have the negative path. So I'm not sure like if we want to use the Bellman fold.
Yeah.
No, but here there are no negative paths. So Dijkstra is one candidate.
And
Because if there are negative path, the Dijkstra could not be a candidate
yes, yeah.
for sure.
Then we have to use the Bellman fold. But here since that we don't have negative paths, so I believe like we have two candidates, Digestra and Bell and Floyd Warshall. Okay,
Bellman
and
also handles negatives.
yeah,
No,
which
but
one?
there is no negative constraint. So all three can
We are
work.
only dealing with the positives one, so we don't need the negative cases.
I believe like you guys continue. I have to leave.
Okay, thank you, Gaurav. So
Okay, so I'm not sure about Floyd Warshall algorithm.
even I am not sure, or a Bellman as well.
Is anybody wants to speak about that? Roger or Puneet?
Yeah, so Floyd Warshall is actually based on the concept that you can have any of the nodes as the intermediate to reach from source to destination, right?
Mm-hmm.
So what you do is you start from a smaller set, like you can reach from I to J using just one intermediate, and at each step you just try to increment the number of intermediate steps, like you want to reach from source to destination, including, like in this case, let's assume you want to reach 0 to 3, where you're considering intermediate node as either 1 or 2. Then you can consider 0 to 3 considering all the nodes 1 and 2 both as the intermediate. So that way you keep building your DP metrics, and at the end what you will find is you reach from source to destination considering any of the remaining vertices as your intermediate. At max,
Also,
at max what you can have is from source to destination n minus 2 vertices in between, right? If you don't have a path from that, suppose from 0 to 3, you don't have a path, suppose going through 2, there's no path from 0 to 2 or something else. So you will have an infinite there, and you're just trying to find the minimum, right? So let's assume the first case, 0 to 1. You have a direct path, so you consider there's no intermediate. 3 is the path to reach from 0 to 1. Next, you consider 0 to 2. Now you have to consider 0 to 2, considering one of the intermediates, like either 1 or 3. For 1, you will check three things. Whether the path from 0 to 1 plus 1 to 2 is less than if there's a direct path. So there's no direct path. The only path to reach there is 3, 0 to 3 plus 1 plus 2. Now suppose there's another path 0 to 3, and there's another path which is 0 to 3, which is of 1 weight. Now to reach from 0 to 2 via either single of the elements, like one of the intermediate elements, it can pass through either 1 or it can pass through 3. In that case, if you have a 0 to 3 also with weight 1, your minimum weight to reach from 0 to 2 will be via 3. Right? This is just for one path. Now you can go to the next step where you consider both of them are your intermediates. Right? But still that will not change your path because you will already have the minimum path directly computed from 0, 3, 2. It's a very fairly simple DP problem actually. If you go through that equation, it'll fairly make a very easy sense. It's the basic idea is that like in Bellman code, the basic idea is any path which is shortest from source to destination cannot have more than the edges that are in the entire graph. Like if you have 3 nodes connected, yeah, the maximum number of edges can be 2, right? You have 0 to 1, 1 to 2, that will be 2.
So I
And
think
then
I think I went in to discuss and somebody wrote the code for this. Or probably you can just see the code and
okay, have you posted somewhere like on Slack?
no, it is in the discuss. If Sonia can open discuss.
Okay. Which
And
one?
the first one.
Floyd algorithm?
Mm-hmm. If you come down to Java, or
Yeah, this one?
yeah.
Yeah, so the entire Floyd-Warshall algorithm is on that 3 loop, like k equal to 0, I equal to 0, j equal to 0. So it is looping from k equal to 0 means it is considering 1 intermediate, 2 intermediate, 3 intermediates, that way, which is the intermediate node that it wants to compare, like 0 to 1, 1 to 2. And then the last line is the basic DP problem. It is just trying to see whether the path that I have calculated till now to reach from I to j is smaller, or if I go through k, it is smaller.
Mm-hmm.
Okay. And this is, yeah.
Yeah, and at the end, what it is doing is just comparing all the cities and seeing which one's distance is less than threshold and counting that.
So it is putting something max value first at the somewhere at the top. Like what would be the max?
Like,
So in
it
this,
will be the
it's
N.
putting 1001.
Could you go up there? It's something, because the values inside the DP are supposed to be only 10,000.
Mm-hmm.
Because it said the maximum distance is 10,000. So that's why it is just setting it one above the maximum value, which is equal in the problem constraints.
So
You can set
it
it to
seems
infinity.
like
You can set it to infinity. Max
infinity.
value.
Okay, so first row is infinity in the DP.
So what it is doing is just saying that the direct path to reach from I to j without any intermediate is infinity at the first.
Mm-hmm.
And then it is trying to build the DP up. Okay, now I'll calculate if there is an edge directly, then I'll set it up as some value. Because there may be some nodes which are not connected at all. So infinity means that they are not reachable from each other.
Okay.
From same edge to same edge. It seems like.
Same edge to same edge means? I'm not sure, right?
Okay, I think we can all go and read this solution and see if that makes sense.
First of all, if anybody wants to understand the Floyd algorithm, I think they need to understand it from other source, and then they jump
The
towards
geek
problem
articles, both Bellman and Floyd are very crisp, and they explain the basic idea why those two are different. One of them works on the basis of edges, and another works on the basis of vertices. So
Do you have
I
any
would,
source where we can
yeah,
read
I can share the Geek for Geek links.
Okay.
Share it on Slack.
Okay. Thank you. Thank you so much, Puneet. Okay, so anyone wants, and anyone has doubts or any question? I think then we are okay for today. Thank you so much. Thank you, everyone. And
Very good night.
Puneet, you want to say something?